I guess we can start. Hi, I'm Ramana Raja, a software engineer at IBM. I work on Ceph's block device component RBD. And with me is Prasanna Kumar Kalever. He's a software architect at IBM. He also works on the Ceph's block device component RBD. So today we'll go over RBD's features and enhancements and important fixes that are in the Squid release and the future plans for RBD. So what's in Squid? We have performance optimizations in RBD that is good for a backup use case. We have rigorously tested the snapshot-based mirroring feature and provided important fix for this Squid release, and it's an ongoing effort to stabilize this feature. And we also improved the usability of group snapshot. So a year or two ago, a community user reported that when using QEMU RBD driver, backup of large RBD images took quite some time. It actually regressed for him. So on investigating, we discovered the diff-iterate API used by the QEMU RBD driver wasn't performant. The diff-iterate API in RBD is basically used to iterate over an image and report byte ranges that differ between snapshots. And so we made performance enhancements to this diff-iterate API. So to make it more performant over when you specify a specific byte range in the API. And also we made changes so that it runs locally in a client when it has exclusive lock, and when you're creating a diff against the beginning of time or since the image was created. So with these performance enhancements, the QEMU live synchronization and block device backup use cases showed significant improvement in performance. To test this, we used the same test case that the community user provided. It was a synthetic QEMU block device backup test. And when we ran this test without the performance enhancements on a 500 gigabyte image, it took approximately 560 seconds. And with the fix, and when the exclusive lock was available to the client, it took close to 3 seconds. And even without the exclusive lock, it took close to a minute. So as you can see, there was really good improvement. For more test results, I've included the link to our tests on larger RBD images as well. You can check it out. Moving on to RBD mirroring. RBD mirroring is a feature that allows you to asynchronously replicate images between clusters. This is useful for disaster recovery applications. You can run the RBD mirroring in two modes: journal-based mirroring and snapshot-based mirroring. Today we'll focus on snapshot-based mirroring. So in snapshot-based mirroring, what you do is you take regular mirror snapshots of the primary image, and then the RBD mirror daemon that runs on the secondary cluster identifies the data and metadata changes between these images, and then just copies over the snapshot delta. So we were rigorously testing the snapshot-based mirroring feature in different environments. And one of the issues we identified was when taking mirror snapshots of the primary image under I/O, and then executing a relocate scenario where we demote the primary image and promote the secondary image. The secondary image was corrupted. So we made changes to the librd and krbd clients to make sure that they don't corrupt the object maps of primary mirror snapshots that are taken under I/O. Snapshot-based mirroring relies on these object maps to create the snapshot delta that is synced over to the secondary. And then when we're running these clusters that are being mirrored in constrained Ceph environments, like Kubernetes environments that we use for some of our products, we realized that the snapshot scheduler that we have in the Ceph Manager module, which allows you to create mirror snapshots automatically, just stopped working. It was getting blocklisted by one of the kernel clients. So we made change to the kernel client to not aggressively blocklist other clients. And we also made changes to the manager module, specifically the snapshot scheduler, to be able to recover from blocklisting. And when there was high latencies between the primary and secondary, we observed that the RBD mirror daemon just stopped working. So we had to fix it so that the operation of removal of the old sync snapshots in the primary, the cleanup of that, be localized to the primary cluster itself. We also observed that in these constrained environments that we're talking about, the latency of the OSD requests was very high. When investigating, we identified the OSDs were spending a lot of CPU cycles on snap trimming. So changes were made to Blue Store to make sure that this doesn't happen, at least reduce it. So that helped with lowering the latency of OSD requests, and it helped with the overall setup. We also enhanced the usability of group snapshot. In RBD, you can create a consistency group formed of multiple RBD images, and then you can take a snapshot. So when you take a snapshot, internally, it creates snapshots of these member images. But we don't have a clone command where you could just clone an RBD group snapshot. Instead, in Squid release, what we have is the ability to clone from these individual member snapshots, and then you need to manually create a RBD group clone from these individual member snapshots. It's not the most ideal way of doing things, but it's what we have. And we also had someone in the user mailing list asking for some way to make use of the group snapshot, clone it. So this is a step towards that. OK, so we have some features that are already available in the main branch. So this should definitely be in the Tentacle release. One of them is enhanced support to RBD's live migration feature. And other is to improve the snapshot-based mirroring feature. So RBD has live migration that allows you to move images across locations almost immediately. So you have almost immediate access to the target image, while the source gets deep copied in the background. This is, in the Squid release, we already have the ability to live migrate images between different pools in the same cluster. So you can move live migrate image from a erasure coded pool and to a replicated pool, for example, and vice versa. And you can also live import images from an external data source. So you can live import from a regular file, from a HTTP file, from an S3 object, and we support raw format and QCOW2 format with some caveats. So what do we have in the main branch? We already have the feature to live migrate images across Ceph clusters. So this is useful for like a plan migration use case or for load balancing. So we do a deep copy of the source image, so you get to preserve all the snapshots and the sparseness. We are also improving the ability to import from an encrypted image. There's still a work to do where we haven't fixed the issue with preserving sparseness when we import it from an encrypted image. Okay, we also introduced a feature that allows us to live import from an NBD export. So basically, you can import from an external source that is through a NBD server. So what this allows RBD is like we can support a wider variety of source formats, those that are supported by the NBD server, and we don't have to be restricted to only those formats, source formats that librd can support. And NBD protocol also preserves sparseness. So this allows us to live import from raw images and preserve sparseness. So here's an example of how we can do that. We can set up a QEMU NBD server and export a QCOW2 image. And then to import it, you specify the stream as NBD, and you specify the URI path of the NBD export. And we also introduced an enhancement to snapshot-based mirroring of images. So you can mirror an image from a namespace, RBD namespace, to a differently named namespace. So this is a building block to create multi-tenancy in a disaster recovery use case. So where you have each tenant restricted to a specific RBD namespace. So to do this, you would, when enabling mirroring on a particular namespace, you would specify the destination namespace using the remote namespace option. So what's next? Work in progress PRs. We want to focus on performance optimizations for RBD. The plan is to leverage the existing core Ceph features, some of them which have been introduced in Squid that we talked about in the morning. For example, the PG upmap read balancer. The PG upmap read balancer feature allows you to optimize the placement of PG primaries across the devices so that you have better read distribution and resulting in higher read throughput. So we want the kernel RBD client to support this to make use of this feature. And in Squid, a new crush rule was introduced, the multi-step retry rule, that allows us to support more cost-effective erasure-coded configurations. So this improves RBD's usability as well. So we want the kernel client to support this crush rule. So this should be introduced in the Tentacle release. And there's already been a lot of talks about erasure coding enhancements. So right now, the erasure-coded pools aren't as performant as replicated pools, especially for small random access performance, which means block and file workloads. So there's been a lot of research and development happening in this area by IBM's UK team. I think they already have code upstream to improve partial reads, and the work to improve partial overwrites is happening. And they also have a nice design document on their plans to improve other I/O patterns performance over EC pools. So I really like the talk at Ceph Day London, so you can check out the recording by Bill Scales. That was really informative to me. And there's also a talk tomorrow by Connor. So if you're interested in delving deeper, and I also heard Jamie's talk like a few sessions earlier, which was great. And we want to improve the protocol support for RBD, the NVMe over Fabric protocol support. As you know, NVMe over Fabric protocol is becoming more preferred over iSCSI because of better performance numbers, higher throughput, lower latency, just a leaner protocol. So we want RBD to support it. There's a talk earlier today by Aviv and Orit about this. You can check out the recording once it's up, the roadmap. So in the Tentacle release, there's code already to make the HA configuration, highly availability configuration for the NVMe over gateway setup for RBD. So there's no single point of failure, basically. And there's continued work to improve monitoring and observability. There's scale testing, and there are features, security features as well, like NVMe inbound authentication and namespace masking. So we also want to continue improving the disaster recovery feature. There are work-in-progress pull requests to support snapshot mirroring of clones and to propagate discards from the primary to the secondary. And we're introducing a big feature in Tentacle that'll allow you to mirror snapshots of consistency group. This is useful for disaster recovery of applications that are backed by a group of RBD images. So Prasanna will talk about this later in the second half of the presentation. So what's next future work? There's a lot of continues to be focus from a development team on the snapshot-based mirroring feature. The snapshot-based mirroring feature already has code to support multiple RBD mirror daemons, but we really haven't tested how good they are at load balancing the synchronization of images from the primary to secondary. And then we want to build in synchronization fairness into the mirror daemon itself so that you don't end up in a scenario where only some images get mirrored, others get left out. And we also want to do a checksum of the snapshots that are getting mirrored. We want to come up with something smarter than just checksumming the secondary image and then you compare that to the primary image and make sure it works. We want to come up with a better way of doing it. and also general usability improvements. There's librd already has a write-back cache, but we haven't. I mean, it's been a while since it's been improved. So we want to investigate that, and we have someone new in the team who wants to improve it. So with that, I'll hand it over to Prasanna, who will give you more details about the snapshot-based mirroring feature.
Hey, thanks, Ramana. That was a wonderful session on the updates. Let's go into more details on the RBD consistency group snapshot mirroring. So let's go through the glossary to see if the terminology fits the rest of the session. So mirroring is kind of like asynchronous replication of data between the clusters. The primary is the active node where the I/O is ongoing and is actually the source for the mirroring. The secondary is the one where we mark it as a read-only copy, and it's actually the destination for the mirroring. The RBD mirroring is responsible to kind of like pull all these changes on the secondary from the primary. Repair is part of the RBD mirroring daemon, which handles synchronization of this data from the primary to the secondary. There are links to the upstream work and the documentation, thanks to Mikola, who kind of like started this work more than 4 years ago. We kind of pulled that from there and then changed the design a bit, but most of the functions which we use remain the same. So as part of this presentation, let's keep it crisp. We'll be talking about why, what, and how consistency group snapshot mirroring. So we right now have a single image mirroring. It's not just enough for the modern applications. Why? Because it just takes care about maintaining the snapshots of one image at a given time. So the modern application might work with more than one disks at a time. So if we have multiple disks, which means underline we have multiple images, how are we going to take the snapshots in point in time of all of them at a given time? So how are we going to take control over the part where these image snapshots need to be mirrored to the secondary, which will be useful at the time of the disasters? And we make sure how we're going to make sure that these image snapshots reach to the secondary before even we hit the disaster. Even if you're lucky enough, and let's say that these image snapshots have already landed onto the secondary, how are we going to restore this particular set of image snapshots? So yeah, let's say your application has kind of like 3 images, for instance, image 1 and image 2, image 3. Probably if you're trying to take the snapshots of these particular images of different time stamps, let's say T1, T2, and T3 respectively, that's not going to be enough. So what's the proposed solution here? We'll go to that in a moment. But let's say, so let's take an example of libvirt VM, where you might be having 3 images, image 1 and image 2, image 3. Let's say image 1 is occupied with your root file system content, and image 2 is used for your application to kind of like persist its own data. And image 3 is where, let's say you are trying to do a logging. Will you be happy if we take the snapshots of these images at different point in time? Because when there is a disaster, if you're trying to restore to this set, you might end up images having in different states. So that's not something that the applications would look for. So this is exactly where we need the consistency group of images. So for disaster recovery scenarios, we need consistency group snapshots to be mirrored onto the secondary. Thus, when there is a disaster scenario, you will be able to restore to this set of consistency group snapshots so that you can resume it from there. So how are we going to do that? So what are groups? As Ramana already mentioned about it, groups are a set of images tied together. They're kind of like a unit of, they're kind of a unit. So the groups generally allow trying to create them, delete them, and list them. Apart from these general operations, groups will also allow you to take the snapshots, allow you to add images, remove images from them, and it also allows you to roll back to a particular snapshot that was taken in time. So what is a group snapshot? A group snapshot is a set of image snapshots within them taken in point in time. And each of these image snapshots will be having a reference to the group snapshot, and vice versa. The group snapshot will also have references to this particular image snapshot in the row. So a group replier is, as I mentioned, is a component of the RBD mirroring, which is responsible for mirroring the groups. But group replier uses an instances of all these image repliers. You might be already aware about image repliers. Image repliers are the one which particularly pulls up the image snapshots from the primary to the secondary. So group replier utilizes these image snapshots and kind of like wait there, allow these image snapshots to be pulled onto the secondary. Once it sees all the image snapshots which are belong to it are pulled, it tries to mark that group snapshot into complete. Here is a naming format which we use for the mirroring group snapshot. It starts with .mirror, and then there is a primary and non-primary label there, which defines where the snapshot is actually created. There is a group global ID and the group snap ID, which remains same both on primary and secondary. Well, the group replier also takes care of unlinking these group snapshots while the mirroring is happening. If a previous group snapshot is already synced to the secondary, it makes sure that when it is no more needed, it tries to remove it. So how are we going to use this consistency group snapshot mirroring? So here is the following set of commands that we have over CLI. These are all backed up with the APIs underneath. We'll be talking about each of them in detail soon. So yeah, let's discuss about each of these operations. So there is an enable and disabling of the group for mirroring. Once you kind of like enable a group for mirroring, it tries to create a primary group snapshot. So the primary group snapshot is the first of its kind on that particular group, which has all the data from the beginning. And the enable also makes sure that you notify it to the secondary so that no secondary is kept informed about it, and it tries to pull the data and even the snapshot there so that all your data is completely synchronized. Well, on the counterpart, we have a disabling of a group for mirroring, which kinds of clears up all that group snapshots and removes the group in total on the secondary. We have add an image and remove an image kind of like functionality, which keeps the groups mirroring very flexible so that you can add an image to it or remove an image to it, which you would like, your application would like to include that in this particular set. So we have a natural operation of mirroring group snapshots. So you can explicitly take these mirroring group snapshot when required, but there is also a group snapshot scheduler which kinds of like creates it automatically on the user provided schedules. Ramana is currently engaged working on that. So we also have a demote and promote group operation. A demote group operation kinds of tries to take the snapshot. We call it as a demote group snapshot that includes the complete set of delta, the last set of the delta that need to be transferred to the secondary. So so primary promoting a group is kind of like marking a group to kind of like primary. A force promote group is performed on the secondary. This is the actual, when you hit actually a disaster scenario, when there is no primary at all, you have no other choice. If you wanted to migrate your workloads to the secondary, you will be able to do that with force promote. Caveat, there is a bit of data loss because there will be no demote snapshot transfer to the secondary in this particular case. So there is a resync group from primary. So the resync is kind of like syncing all of that group from your primary to the secondary. When you feel that your group on the secondary is stale, for example, you take an example of a disaster where you see that there is stale data on the secondary and you wanted to resync it completely, which involves deleting the group on and all, and try to create it. We have more scenarios of relocate, failover, and failback. Relocate is planned failover. It's like you demote the primary and promote the secondary. It's a plain use case which probably is used for maintenance and load balancing. A failover is issued on a real disaster scenario where you might want to force promote your secondary because your primary is no more available. On a failback case, you see your previously disaster hit cluster is back online, and you wanted to bring back that and kind of like wanted to fail over. Let's go through a demo, a short demo, where we'll be talking about how a mirroring of the group from primary to the secondary is happening. We'll see how a relocate can be issued, and we'll also see how a failover can happen in case of disaster, and see how we can fail back to the previous cluster. Demo, please. You can see first, in the first case, we'll try to create a group. We'll enable it for mirroring. So this is a plain case where we are trying to see if the group is mirroring to the secondary. We can check the status of the group on secondary and try to see it is upless replying, because RBD mirroring is trying to pull the data, and primary will be staying in upless stopper state most of the time. So we try to add an image to the group and see if that's actually getting mirrored to the secondary. Well, we have the complete set of group enabled for mirroring. Here is a flexibility of adding an image to already enabled group. So we can see that once we add that image, the image is also kind of like mirroring to the secondary. It's an upless replying state. Now you can see the snapshot, group snapshot list. Note down about the last 2C6D ID, the last group snap ID, and make sure that's matching on the primary and secondary, so that data is in sync. So the list of images on the group, just to showcase, we have image one both on primary and secondary. Now try to list a pool, the test pool, and see if the same thing is displayed there. Yeah, we can see that test image one is mirroring successfully. Now let's try to do a relocate operation. So this is a simple relocate operation. So we will try to demote the primary and wait for the snapshots to be synced completely, because the demote snapshot is the final snapshot which is having all your delta there. So once you kind of like demote, there is no secondary now, so there is no upless replying. You can see that both the clusters are in upless stoppered state. And if you list the snapshots, you wanted to check that both the snap IDs match there, so and the both are set to be complete. Now you try to promote the secondary and see that's getting reflected on the status. Well, you can see that the upless replying is happening, which means that it's the relocate is happening fine. You can list the snapshots, the group snapshots, and see both are matching again. Well, that's a successful relocate operation. Now let's try to add a new image because we already relocated. So on the side B, we are trying to add an image to the mirroring group, and see that's already mirrored pretty fine. Yeah, we're trying to check the status. Yeah, you can see the both images are now replying. You can see that again the group snaps should match all the time, and they should be marked complete. That's how you get to see that your data is it's not missing anything. So you try to list the images in the group. On site B, it says 2 images are there. On site A, it should say 2 images are there. Well, that's taking place. Now you can see the the pool. You can try to list the pool. Yeah, even on site B, there are 2 images in the pool, and even on site A, there are 2 images on the pool. Now, assume we'll go through a different scenario of disaster. Assume there is a disaster on the primary, and we'll be failing over to the secondary. Now, so as part of the failover, we'll have to issue the force promote. So I have just issued the force promote. Since there is no secondary now, all will be in upless stopped state. Yeah, we'll try to continue the workload even after we kind of like fail over. We try to write some data there. We try to take the snapshot. So this data is, the delta is already copied, is there. So assume the site B is back online now, so we need to demote it, because we know site A has performed quite a bit of I/O operations there. So once we kind of like demote it, we see a split brain because there is a data mismatch. You can see that it's an upless error state, and a split brain is detected. You can see the snap list now, they won't be matching, because we have a split brain scenario here. Yeah? The snapshots are no more matching. So we will need to do a resync here from the primary. So I'm marking the group for resync. Wait for a second, and you see the status now, because we already issued a resync that's happening. And you can see the 2 of the images are in upless replying state, and the group itself is in upless replying state. Now try to do a snap list on both the on both the clusters. You see they are matching now, because the resync has happened. We can now the resync has happened, and both the clusters are good. We can actually do a failback. So for the failback, again, you need to do a demote on the primary, and you need to do a promote on the secondary, which was site A here. So we promoted site B, so it's back online. So you can see this upless replying happening for both the groups. Sorry, for both the images. And you can see the snap list is finally matching. Yeah, that's it. Thank you. We are open for questions if there are any. That sounds like a no. Thank you. Yep.
Was wondering, your example of image 1, 2, and 3, two group snapshots, there could be a delta when the first one completes until subsequent 2. Is there any way to see how much of a skew there is between the 2? Or is there any type of expected max delta that you might run into?
Yeah, so the question is about the stats, to see once you actually created a group snapshot, you wanted to see the stats where how that entire group is mirroring to the secondary. Is that right?
When you create the snapshot, the group snapshot, one could be skewed potentially. How do you monitor? How are we able to see if something, for some reason, is overreading all the time?
Well, yeah. So yeah. So what generally happens is we have the group replayer on the secondary, which tries to pull these image snapshots to it. So just in case if any of these image snapshots are not yet pulled there, we are going to still maintain that group snapshot in incomplete state. We are not going to mark it to complete until all of the image snapshots are synced to the secondary. So even if there is a disaster in such scenarios, we kind of like going to pick failover, do a rollback to the previous group snapshot, which is in a complete state. Does that answer your question, Chris?
So you're talking about the actual syncing process. I'm wondering about just the actual between, maybe this is a moot point, but between on the primary side, the group snapshot, what happens with if the images take different times to actually snapshot, which can happen sometimes.
You mean there is a bigger snapshot as part of the particular group? So one image is probably having a lot of delta and other images are having less data. How are we going to handle the scenarios? More or less? Or is it a question about the stats? Right? We can catch offline, Chris. Yeah.
I think that what he asked is, do you take all of the snapshots exactly at the same time, like at the same millisecond or microsecond?
Yeah, so right now, so the goal is that, but right now we actually loop over the set of the images that we have right now and try to take the snapshots in that particular time. But the goal is to do that.
Maybe take the, try to get the exclusive lock and.
Yeah, yeah. You wanna
No, it's okay.
Thank you.